Hi everyone, let's go and work on this problem number 6 in problem set 8. This is a question about lattice energy and specifically calculating the value of lattice energy using something we call the Born-Haber cycle. Now, this problem is actually asking us to calculate the enthalpy of formation for magnesium fluoride, whose reaction is given right here, Mg in the solid state plus fluorine gas forming magnesium fluoride in the solid state. However, one of the components here is lattice energy. And so if you want to think about this problem in general, this is a Hess's law problem where you need to come up with a set of reactions and to add them such that you get that target reaction that's given at the top. However, the series of reaction that's involved here is what's known as the reaction in the Born-Haber cycle, as I just mentioned, which is typically a set of reactions that we use to help us figure out the lattice energy of a particular ionic compound. So again, the question is, how do we write all these reactions in such a way that when added up will give us that target reaction that's equal to the enthalpy of formation reaction? Okay, to do that, we're going to have to write each of the reaction given by the energies written here. So the first one is that lattice energy. So you remember with lattice energy, that reaction corresponds to the following. It's a reaction between a cation and an anion in a gas phase forming its ionic compound in the solid state. So since our ionic compound is magnesium fluoride, our two ions is going to be magnesium ion, magnesium 2 plus, in the gas phase, plus the fluoride ion, two of them also in the gas phase, forming magnesium fluoride in the solid phase. So that's what lattice energy reaction looks like, and in this case the lattice energy is 2913 kilojoules. And then the first ionization energy of magnesium. Well, ionization energy refers to the energy needed to remove an electron, so I'm going to write it for magnesium. That would look something like this: magnesium in the gas phase going to magnesium ion, but only plus 1 in the gas phase, plus 1 electron. So 1 electron is removed in this case. So that would be called the first ionization energy, and it's a positive number, 735 kilojoules. And then the second ionization energy follows right after, and so that one is just going to be Mg plus. Now taking out another electron, so it becomes Mg2 plus electron. This is second IE, and that's 1445 kilojoules. Now another reaction that's given there is the electron affinity of F. Electron affinity refers to a reaction where something gains an electron. So in this case, since it's talking about electron affinity of F, that means F is gaining an electron, forming F minus, all of these in the gas phase. So this delta H is delta H of the electron affinity, and that's negative 328 kilojoules. And then the next reaction is called bond energy of F2. So bond energy or bond enthalpy refers to the energy needed to break a covalent bond. So you go from F2, which is a molecule in the gas phase, to 2F, which is the atom. So you take the molecule and you break it into the two atoms. So that's your delta H of BE, or bond enthalpy, and that's 154 kilojoules. And then the last one is enthalpy of sublimation for magnesium. Sublimation refers to the fact that you're converting a solid to a gas. So you take solid, make it to gas, and that's our sublimation. The value is 150 kilojoules. So the question is, can we add all of these reactions such that they would give us the reaction of interest, which is given at the very top here, the formation reaction. Now let's see, some of these things we can cancel out, as you can see. So first off, I can cancel out my magnesium 2 plus in the gas phase. Can also cancel out my magnesium plus, magnesium gas here, and way at the bottom there's one there. And that's pretty much it for now, except that we can try to cancel some other stuff out if we multiply one of these reactions with the right number. So if you notice here, there's 2 electrons on this side, and then there's only 1 electron on this side. So if I can make it 2 electrons on both sides, I can cancel them out. And the way I can do that is I can multiply this reaction right here by 2. So I put 2, 2, and 2, which means my electron affinity value is going to be double. And when I double that, I get negative 656 kilojoules. And so once I have that, now you see that I can cancel out the electrons, 2 electrons on the right, 2 electrons on the left. Not only that, the 2F gas cancel out, and then the 2F minus also cancel out, one in product, one in reactant side. So what's left in the end? Well, let me circle those guys. You got an F2, you got a Mg, that's on the reactant and the product, so you got MgF2 in the solid phase. So let's add all of these together. Magnesium solid, fluoride fluorine gas, magnesium fluoride solid. And so what I have to do is just add all these numbers together. Don't forget that I'm going to use this negative 656 with the electron affinity since I multiply it together. And so that reaction, of course, is a formation reaction. And so after I add all of these up, I get 1085 kilojoules. So that's the enthalpy of formation for magnesium fluoride.